people normally associate with toxic or poisonous substances. There should almost be a different word for it because we're operating in a different regime. The kind of toxicity that we see from cryoprotectants used in vitrification solution, at least for reasonably well-chosen ones, is a toxicity that results from replacement of water around biomolecules. So basically what seems to happen is once you cross a threshold of around 40 or 50% replacement of water around proteins and possibly other biomolecules, something happens that affects their ability to recover their normal function when the cryoprotectants are removed. And we don't know whether it's protein denaturation or something more subtle, but there's something that's related to, some problem that's related to replacing so much water in biological systems. So what we would really like, the ideal cryoprotectant would be something that would look just like water.
Something that mimics water.
Biomolecule, but that wouldn't freeze. So in a sense, that's what we try to do when we choose cryoprotectants in vitrification solutions, is choose chemicals that look as most like water as possible, but that prevent water from freezing.
Yeah, I suppose that is a you know, it just dawned on me again, yet again, how difficult of a problem that is, being that water is a small and unique molecule in its physics.
Yes.
Yeah, boy. Yeah, tough problems here.
It limits the design space because the smaller a molecule must be, the fewer ways there are to put together atoms to make molecules that size. So the number of choices is rather limited, unfortunately.
Yeah. Well, and that makes me think about another problem that I know occurs during the chronic preservation of human bodies, and that is large fissures that occur in organs or perhaps the brain. Is that another significant stumbling block, or is that something that is going to be perhaps more easily dealt with say, future technology? I mean, I hate to speculate too far into the future, you know, how patients are going to be recovered, but are those fissures that develop once it gets once a patient is cooled down to liquid nitrogen temperatures, is that a major problem in your view?
There are two ways of addressing that question. There's the question of prevention, and there's the question of treatment. As far as prevention goes, preventing fractures, that's one of the easier problems to deal with because it's a pure physics problem. If, at least for smaller organs, if you use the correct cooling protocol and storage temperature, you can avoid fractures. In fact, I myself have managed to cool rabbit kidneys all the way down to liquid nitrogen temperature, keep them submerged for 2 weeks under liquid nitrogen, and then rewarm them with no fractures whatsoever if the correct cooling and warming protocols followed. And it gets trickier as you go to larger organs, but
because of thermal stress.
It's a pure mechanical stress issue, and if you cool correctly, you can minimize that stress. So as far as prevention goes, it's one of the simpler problems that I think vitrification of large organs and tissue faces. Now, as far as the treatment question goes and prognosis for cryonics patients, etc., I don't lose too much sleep over it because I don't think it actually causes loss of information. When these fractures form, they're forming at cryogenic temperatures when the material is already solid. In fact, solidification of the material is sort of a precondition for fractures to form, which means that when a fracture face forms, the faces would be expected to be clean and matching, which means whatever future repair devices you imagine going in there to infer the original structure and information would probably have complete information to work with. So I'm not too concerned with it from a point of view of information loss. I'm a bit concerned about it from the point of view of the level of technology that's required to repair them, meaning that I think patients with fractures might have to wait for a higher level of technology to come along to do the analysis, to do the repair, but I'm not concerned about it in terms of loss of information.
Okay, yeah, loss of information, not so bad. Yeah, I was thinking about it from a biological perspective. Say we had the capability to freeze someone with zero toxicity toxicity or vitrify someone, and then revive them. And if they had those fissures, I was just wondering if, I was thinking to myself, are they small enough that normal bodily repair mechanisms would find their way of repairing those fissures? You know, that just a little cryonics question that had popped into my head. But
yeah, no, they wouldn't spontaneously heal, so they would require something to go in there and put things back together again. So they would require some quite high level of technology to fix. And I think what's going to happen, though, is as we get better and better at reversibly cryopreserving large organs, that there will be a commensurately greater level of attention devoted to thermomechanical issues like fracturing, and we'll see these things solved. In fact, that's sort of already happening.
Okay.
There's a group at Carnegie Mellon University that several years ago got a multi-million-dollar grant from the federal government to study thermomechanical aspects of fracturing and vitrified systems, and they've begun to publish extensively on that. And so there is work being done in that area, even outside of cryonics.
Oh, that's good to hear, yeah. I want to go to a couple of questions that have come up. One that I think I can answer here: can organs be cryonically frozen and then thawed out and successfully implanted? I'm familiar with your work with the rabbit kidney, I believe that was, and to the person who asked the question here, Dr. Wowk successfully vitrified a rabbit kidney and then brought it back, implanted it back into a rabbit, and it did have some functionality, correct, Dr. Wowk?
Yeah, it had enough function to support the life of the rabbit as the sole kidney for a period of 40 days, at which point we just basically said, okay, this experiment is a success. And by the way, the primary credit for that goes to my colleague, Dr. Gregory Fay, who's been working on this problem of kidney vitrification for 30 years now. And we're continuing to develop that. And in fact, we're coming out with a paper on that in a few months.
So the answer to the question, at least in an animal model, it has been done. It has been frozen down to liquid nitrogen temperature and then returned to viability.
Yeah, and I should mention that other organs have been done as well. Ovaries have been successfully vitrified and reimplanted with function. And in terms of technologies other than vitrification, there's a rather famous example of canine intestines being frozen and reimplanted with subsequent function decades ago, actually. So even with freezing, there are some organs that can survive freezing and reimplantation, although vitrification is then generally the preferred method.
And another question, I'm not sure if you are familiar with this, but I'll give it a shot anyway. A member from Europe, audience member here, was on the cryonics mailing list and heard someone suggest using ionic liquids as cryoprotectants. Now, I haven't seen this particular mailing list or I'm not familiar with this suggestion. Is that something that you've heard or looked into?
Yeah, this suggestion was just made a few days ago by Mike Darwin on the European cryonics mailing list, and you couldn't perfuse a pure ionic liquid into an animal because there would be severe osmotic dehydrating effects from that. So the question then becomes, can you use ions as minor ingredients in a cryoprotectant solution? And from the point of view of using them as minor components, it really doesn't matter whether they're ionic liquid ions or any other kind of ions. It's just a question of, can ions be cryoprotectants? And the answer, as I indicate on that mailing list, is that the ions can be used as minor components, but generally aren't used as major components in cryobiology because they don't penetrate cells very well. So they're sort of confined to the extracellular space, and that limits their utility.
All right, well, we kind of talked a little bit here about the science of cryonics and what's coming in the future, what we have in today's day and the present day, let's say. What about the other part of cryonics, and that is social acceptance? And what I usually say when it comes to radical life extension, from what I've seen anyway in my work with the Institute, is that I'd have to say 50% of the problem of radical life extension, and I'm sure it perhaps goes to cryonics as well, is